students, welcome again to our YouTube channel. Today we are going to discuss about Hund's rule of maximum multiplicity. Hund's rule of maximum multiplicity. Hund's rule of maximum multiplicity. What is defined by this rule? This rule says that degenerate orbitals first get singly filled then pairing occurs. Means the degenerate orbitals. Now what are the degenerate orbitals? Degenerate orbitals are those orbitals which are having the same energy. That means the orbitals which are having same n and l values. Same n and l values. Now this rule says that degenerate orbitals first get singly filled, then pairing occurs. That means when you go to fill up the orbitals of an atom, then if the orbitals are having same energy, then what will happen? We have to fill up each orbitals first with one electron, then we will move for the second electron, or we have to move to pair up the orbitals with the electrons. Let us consider one or two examples, just like carbon, nitrogen and oxygen. We have the atomic number of carbon is 6, nitrogen is 7, oxygen is 8. Now, we have discussed our Auber's principle, also Pauli's exclusion principle. From Auber's principle, we have seen that the orbitals are filled up in order of their increasing energies. So, first we have go to 1s, then 2s, then 2p in order of their increasing energies. In case of nitrogen also 1s, 2s, 2p. In case of oxygen 1s, 2s, 2p. Now we know that from Pauli's exclusion principle, one orbital can accommodate a maximum of 2 electrons. Only two electrons one orbital can accommodate. Now here s orbital can accommodate 2, here s orbital 2, here p orbital can accommodate a maximum of 6 electrons, as p is having 3 orbitals. P subshell is having 3 orbitals, as s subshell is having only 1 orbital. Similarly here 1s only 1, 2s only 1, 2p 3 orbitals. Here 1s 1, 2s 1, 2p 3 orbitals. Now this p orbital can accommodate a maximum of 6 electrons. Now if 6 electrons it can accommodate, then what happens in case of carbon? We can see that here 6 electrons are available in case of carbon. So first 2 electrons we will give to 1s. More than 2 electrons cannot be possible, that we have known from our Pauli's exclusion principle means an orbital can accommodate a maximum of 2 electrons, means only 2 electrons can be given in an orbital. Now in case of 2s also we can give 2 electrons, so 2 plus 2 4, 2 2 4 we have given here. Now 6 minus 4 we are getting only 2 electrons. Here 6 electrons are present in case of carbon, so 2 electrons we have given in 1s, 2 electrons we have given in 2s, so 4 electrons already gone. So 6 minus 4 we are having now 2 electrons. These 2 electrons we have to put in 2p subshell. Now in 2p subshell we have 3 orbitals. We have 3 orbitals in 2p subshell. 3 orbitals, 1, 2, 3. So if these 2 electrons we may give like this, or we may give it like this. Here you see both are having parallel spin. They are present in different orbitals, whereas here in the same orbital. Now our Hund's rule of maximum multiplicity says that degenerate orbitals, means these orbitals, these and these two orbitals are having same energy, means they are degenerate orbitals. So this rule states that degenerate orbitals first get singly filled, then pairing occurs, means first we have to fill up the orbitals with 1 electron each, then if more electron remains, then we have to pair up the electrons in those orbitals. Now here you see, if we put like this, if we put the electrons, these 2 electrons like this, then what happens? Here in the same orbital we are pairing up without filling up each orbital with 1 electron. Here we have given the 2 in the same orbital. This is not possible, as this Hund's rule states that orbitals will be first singly filled, then if we have another electron, then we may put it in this orbital, then if we have another electron, then we may pair up those electrons. Now here only 2 electrons are present, so if we give these 2 electrons in these 2 different orbitals, then what happens? Our electronic configuration or our electronic arrangement orbital in different orbitals of carbon atom is already done. So in case of nitrogen we see here 7 electrons are present in case of nitrogen. So first 2 electrons we will put in 1s, rest 2 electrons we can put in 2s. Now what happens? We have another 3 electrons, means 2 plus 2 4, so another 3 electrons are present in nitrogen. So these 3 electrons we may put in 2p orbital, 1, 2, 3. This is correct, whereas if we put like this 1, 2 and 3, then what happens? Our Hund's rule is not obeyed, because each orbital must have to get 1 electron each. This is not possible. We cannot put here. We cannot put it here. We cannot put like this. We have to put like this, means we have to give 1 electron to each of the orbitals first. 1 electron to each of the orbitals first, then we may come again to pair up the electrons if we have more number of electrons. In case of oxygen, what happens? Here 8 number of electrons are present, so we may put first 2 electrons in 1s, there's 2 electrons in 2s, then another 2 plus 2, 4 electrons are present in 1s and 2s, so the rest 4 electrons we may give it to 2p. We may give these electrons to 2p. So what we have to do? First we have to go for 1, 2 and 3, then we have to pair up this. Then we have to pair up this orbital. So each orbital first must have one electron each, then we may pair up the first orbital with another electron. This we cannot write like this. This 1, 2, 3, 4. It is not possible. It is not possible. This is correct. So here 2 electron. In case of carbon we see 1s2, 2s2, 2p, 2. Here 2 electrons. In case of nitrogen 1s2, 2s2, 2p, 3. In case of oxygen 1s2, 2s2, 2p, 4. So we may proceed towards writing the electronic configuration of different elements. Now we may see another thing, that why we have to do like this, why we have to put in different orbitals first, the electrons in different orbitals first, then we have to pair up. The reason for this is that we know that electrons are present. Electrons are present. Now we know electrons are having same charge. These electrons are having same charge. So if the same charge, we put the same charge in the same orbital, then what happens? Repulsion arises. In different orbitals, when we put, then this repulsion can be minimized. And if we minimize this repulsion, then what we will achieve? The lower energy state we will achieve. Because if repulsion is more, then energy will be higher, which leads to instability, means which leads to make it less stable. Whereas when we put in different orbitals with similar charge of electrons, then what will happen? This repulsion will be minimized and stability will be more. Now this putting these orbitals, when we fill up with electrons, when we fill up different orbitals with electrons of parallel spin, then what happens? They will move as far apart. So repulsion can be minimized when we put up them far apart. There is some distance, where here you may see that the distance is very less, here distance is very less, repulsion is very high. So by putting them far apart, we may minimize the repulsion, and if we minimize the repulsion, then their stability becomes higher as energy becomes lower in those cases. So we have at last understood the 3 different rules to describe the electronic arrangements of atom of an element. First one we have seen Pauli's exclusion principle. Second we have learnt Abba's principle, and third we have learned this Hund's rule of maximum multiplicity. Our Pauli's exclusion principle states that no 2 electrons can have the same set of 4 quantum numbers. So we cannot get the same set of 4 quantum numbers for the 2 electrons present in an atom. Up to 3 quantum numbers we may get the same. Up to 3 we may get same set of quantum numbers, but the 4th one must have to be different. From Abba's principle we have seen that orbitals must have to be filled up with electrons in order of their increasing energies. Means first we have to give the electrons in the lower energy orbitals, then we have to move to the higher energy orbitals. So we have seen that 1s orbital is having lower energy than 2s orbital, then 2p, then 3p, like this, then 2p, then 3s, then 3p. Means 1s, 2s, then 2p, then 3s, then 3p, like this, then 4s, then 3d, like this. We have seen the different orbitals in order of increasing energies. in order of increasing energies. Means we have seen 1s, 2s, 2p, 3s, 3p, 4s, 3d. Like this, energy increases, we have seen from Abbott's principle, and by applying N plus L rule, we have seen that 1s, then 2s, then 2p, then 3s, 3p, 4s, 3d. Like this, our energy of the orbitals increases. So we have to fill up first 1s orbital, then we have to fill up 2s. Here we have filled up 1s, then 2s, then 2p. Means then 2p, then 3s, then 3p, then 4s, then 3d. We have to move like this. Now from this principle, what we have seen means Hund's rule of maximum multiplicity. What we have seen, we have to fill up the degenerate orbitals, means those orbitals which are having same energies. You see p subshell is having 3 different orbitals, 3 of orbitals, and these orbitals are having same energies. So these are known as our degenerate orbitals. Degenerate orbitals which are having same energies. Now you see here n value is 2 for these 3 orbitals. N value is 2. L value is for p orbital, L is 1. So n and L value are same for these degenerate orbitals, means the orbitals which are having same energies are degenerate orbitals. So degenerate orbitals first have to be singly filled. Then we have to go to pair up the electrons. Means we will move towards pairing of electrons only when each orbital of the degenerate orbitals, each orbital of that subshell is singly filled. Means if each orbital of the degenerate orbitals or of the subshell is singly filled, then we can move towards pairing of the electrons. That is stated by Hund's rule. Degenerate orbitals first get singly filled, then pairing occurs. Means first we have to fill up each orbital with one electron, then we will go to pair up the orbitals with another electron, and this is due to the electronic repulsion, also due to the spin. Also, if we put the parallel spin, if we put the electrons with the parallel spin, then we will get the maximum stability. If we put the electrons in different orbitals, in different degenerate orbitals with the parallel spin, then also we will achieve the maximum stability. So, and if we put these electrons in different orbitals without placing those in the same orbitals, then electronic repulsion will be minimized and our stability will be more. So first we have to fill up the orbitals with one electron each, then we have to move towards the pairing up of the electrons. So thank you.